All right. So, oh, do you guys need another minute? Want me to stop?
You're doing that.
I'm just going to look over number 1, or part A. So, f.dr. So your r is cosine, sine, and t from 0 to pi. So the first thing you got to do is find r prime, right? So r prime, negative sine t, cosine t, 1. And then you need to rewrite f in terms of r. So, well, technically in terms of t. So you would end up with an f of negative sine t, cosine t, and then 3 times cosine times t squared, right? So you end up with, there's my f of r of t, and there's my r prime. So my f dot dr was 3t squared cosine t plus 1. So now you have the integral from 0 to pi of 3t squared cosine t plus 1, which I did a tab method and did it that way. I think this would have also worked okay in polar. I didn't try it in polar, so I don't know. Did anyone else try it in polar? Or did you just stick with, I don't know. Anyway, I got an answer of negative 5 pi. Negative 5 pi. Negative 5 pi, negative 5 pi. You guys are so smart. Negative 5 pi, negative 5 pi. Negative 5 pi. Every single group got negative 5 pi. So well done. All right, 1 down. Look, and I see a tab method right here. That's beautiful. Okay, good job. All right, so part B, same thing, same method. So your r prime would be negative 2, 0, and pi, which is nice, all numeric, I like that. And then you rewrite f in terms of r, and we're going from 0 to 1. So there's my f in terms of r, there's my r prime. So my f dot dr cleans up to be 3 pi squared times t squared minus 2t cubed. Really easy to integrate, just a simple little polynomial. Integrate, plug in some numbers, and you end up with negative 1/2 pi cubed. Perfect, 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 perfect. Yes.
No longer perfect.
Oh.
And
Yeah.
yes, because that's 1, 6, 3, 6. Yeah, wait, it's negative. Yeah. Yep, you got it. 100%. You guys got 100%.
Yeah,
Now. So what are we doing today? Today we're doing section 16.6, parametric surfaces. We have 1 day on this section. There's one part of the section I have a little more time with, and we're going to just kind of breeze past it. We'll do it, but I'm not super in-depth. I'm really bad at it. Maybe as the years go by, I'll get more in-depth with it. But anyway, so 1 day on this, and then Monday and Tuesday we do surface integrals, kind of similar to line integrals, except with surfaces. Tuesday is really an application of surface integrals called flux. Then Wednesday is Stokes' theorem, and Thursday is divergence theorem, and then Friday we're going to just have another quiz day. So if you're out a week from today, the Friday before break, let me know in advance and I can give you the quiz as take home. So, all right, let us begin. So far, we have used vector valued functions to represent curves in space. We also know that to move from curves to surfaces, we need to add variables. That's what we're going to do now. So we've been doing these parameterized paths. So with one input parameter, now we're going to move to a parametric vector with 2 input parameters. So we've got, so r of t, instead of representing like a path along a line or a curve through space, now r of t, or I'm sorry, r of u comma v is going to actually represent a full 3D surface in space. So we're going to represent the shapes that we represented before, kind of with our, we've done this, we did surfaces in Chapter 13 was when we started with f of x comma y, where z was a function in terms of x and y. So z is a function in terms of two variables. The only difference is that now our output is in vector form. That's really the only difference. It's still just a function of two variables, but now it's a vector with an x and a y and a z, and these variables are inputs, but you can kind of go like u, v, z of uv, like if you wanted to, right? You can kind of cheat and do it kind of the way that we did it in chapter 13 if you're really stuck, right? Which I get a lot trying to write these, so anyway. Okay, so first thing I'm going to do is show you a couple of examples of parametric surfaces. So this first example, r of uv, is the vector 3 cosine u, 3 sine u, and v. Now what does that mean? It means x equals 3 cosine u, y equals 3 sine u, and z equals v. Remember, u and v are just variables, right? So let's say u is bounded between 0 and 2 pi, and v is going from 0 to 4. Can you figure out the shape that is produced by this parametrically defined surface? Rishi's nodding. Just hold that thought for a minute. Yes, please go to the nurse's office. I hope you feel better. Go get some rest. Stay in bed all weekend. Don't go outside, it's cold. Drive safe. It's snowy. Okay. All right, any ideas? What do you think? Yes, Dorsa. A cylinder. Does anyone else agree? What do you think? Yep. Rishi's not raising his hand, but he's like, yep. Yep.
I got food.
Yeah, yeah. Ian raised his hand. Yeah, he's gotcha. All right. So the three of you agree that it's a cylinder. Nobody else?
I don't agree. I think it's a cylinder.
Okay. Well, you think, and then those two agreed with you.
Yeah, they're in concurrent basis.
Okay. So, but everyone else totally rejected it.
Yeah.
So.
That's the story of my life.
Yeah.
I feel like it's like a spiral.
So a spiral would be if it's following along like a wire, like we've had in the past, but now it's a full surface. So you're right. If it was 3 cosine t, 3 sine t, and t, then it would be a wire. But because we've added another variable to it, now we do end up with a cylinder. Woo! Okay, so your u is basically just theta. Like you could think of it as 3 cosine theta, 3 sine theta, right? And then your z could just be v, right? It's just your z, right? So really, what is this? This is a cylinder with a radius of 3 that has a height of 4. It's going from 0 to 4, right? Okay. All right, let's see if we can guess another one. Okay. R of u comma v equals sine u cosine v, sine u sine v, and cosine u. Now I have a hint for this. Do you want the hint, or do you want to not have the hint first?
I need a hint.
Hint? Pranav, do you want the hint or not? No hint yet. Okay, I'm gonna give you 30 seconds. Okay, well, there's the hint. V goes from 0 to 2 pi. Oh, I lost my recordy thing. Where did it go? I can't pause it. So we're just going to record. All right, so hint. Think about the value of x squared plus y squared plus z squared. That alone, just looking at that, should be a hint of what it is without even doing it.
I'm so confused with what this is representing.
Oh.
So, you know how we had, God, I'm not so bad to pause it. All right, I'm just going to talk. So, you know how we had, you have a path. We had like RT. and it's a vector, and you plug in a t, and you get out a point, right? And that point, x, y, z, that point is some point on a line, and you follow all the points, right? And you're following along the line. Well, now, instead of plugging in a t, you're plugging in two things. So you're plugging in a u and a v. So what ends up being generated, and this is where I'm not smart enough to really explain this well, is instead of a line, this vector produces points on a surface. So you get, the problem is that the two input variables like aren't x's, y's, and z's, and so I can't explain it without saying there's some other plane out there with u and v that we're plugging values into like to create this surface somehow.
Like how t represents time.
Right, and t isn't on the x, y, z, it's just a thing.
Yeah.
That's, now we've got u and v, it's the same thing, it's just, now it's an ordered pair you're plugging in, and so you have infinitely many ordered pairs, and so you end up creating this full surface. Because even if you hold u static at one value, you have infinitely many values for v you're plugging in, and vice versa. So you get this giant number of ordered pairs that you're plugging in, and you end up producing a surface.
And so that the vector represents like x, y, z.
Yes.
The plane?
Yes.
Right.
This is x, y, z. This is your output.
Okay.
And it's still just going to be a point, right? But you're plugging in now two different things to produce all those points. And if you put all those points together now, instead of producing a wire, you're actually going to get a shape.
Okay.
So I probably didn't say it great, but that's my basic understanding of it. All right, what shape do you think of when you see x squared plus y squared plus z squared? A sphere, right? This is a sphere. Now, the thing that's interesting that made me think of this is, I don't know if you guys remember this or not, but when we learned spherical coordinates, no? Yeah?
Yes.
Right? We learned like the x, the y, and the z values just with rhos and phis, but the exact same formulas, right? So you could think of u as u is rho and v is phi, if I'm saying that right. Anyway, so it's basically just a conversion to spherical coordinates, right? Just like that's really just a conversion to cylindrical coordinates. So anyway, okay. So those two shapes, it's just those are just examples of surfaces. The next one, right, that we're going to try to do, there's an easy way, and then there's the way that like mathematicians want you to do it. So, but I don't care, right? I'm fine either way. Most of the parametric surfaces that you have to deal with will already be given to you. You won't have to figure it out. But for this, suppose we had to write an R of u comma v for this cone right here, right? So see if you can come up with an R of u comma, any R of u comma v that would produce this cone. It can be anything at all. It's easier than you think. You don't have to do it with trig. You can just do it straight up with u's and v's. Did I get my recordy thing back? Where did it go?
Maybe it cancels.
Yeah,
All right, I can go pause. All right, so you could do it x, y. I don't know why I kept it x, y, but you could have R of u, v equals u, v square root of u squared plus v squared. There's our function, two variables, done. So if you're really stuck just let u be x, let v be y, and then write the z in terms of u and v, right? So that's the kind of like the easy way out if you're really stuck. However, this cone can also be written in a trig form, and you get u cosine v, u sine v, and u. That's right. You could again think of this kind of in spherical coordinates where it's rho cosine phi, rho sine phi, and rho, and you're just going out forever, right? And you just get this cone that goes forever. Anyway, if you think of it in spherical, but you know, that's an alternative. Again, I'm really, really bad at this. This is the part that I've been dreading like all year. So I will someday get better at this, but it's not today. So anyway, okay. There is a way, there's this cute little program where you can enter parametric equations in multiple variables. I think you might be able to do it in Grapher too, but I found this really cute thing where you can enter parametric equations in multiple variables and then check to see what the graph looks like. Do you guys want to see it right now or no? Okay. All right. So yes.
So are u and v just placeholder variables?
U and v are your input variables. They're like, you can call them parameters. They're input parameters. Just like t is an input parameter. When you're in R of t, right? T, we were just having this talk. You don't see t anywhere in the x, y, or z world, right? It's just a thing you plug in to produce the points. U and v, again, are just things you plug in to produce the points. And then this output would just be your points, right? The set of all those points. Oh, whoop, yes.
Yeah. So if you plug in a u and a v, like let's say u and v is like 1, 1, are you
Yes.
going to get the same exact point from both equations? Like the trig point and the just like easy way?
No, this u and v would be defined completely differently than this u and v. That's why I really shouldn't call this u and v and this u and v in the same problem, because they're totally different
So they
things.
just like
Two random input parameters. This u and v represents like x and y in a rectangular form. This u and v represents rho and phi in a spherical form. So you can't really equate them because they're different. They relate, but they're different. Okay, let's get into the stuff that I'm like comfortable with. Okay, and this is actually what you're going to see like on your quizzes and your tests and in your homework and everything. All right, so every parametric surface has two partial derivatives now, because all of your functions are going to be defined in terms of u and v. So you're going to have a partial u and you're going to have a partial v, right? So an r sub u and an r sub v. So if you have an r sub u and so I don't know if you guys remember this from way back in like chapter 13 when we were first talking about tangent vectors. So if you hold v constant and you do r sub u, you get, which is what you do when you do r sub u, you get a tangent vector in the direction of u. And if you hold u constant and do r sub v, you get a tangent vector in the direction of v. I'm just putting it in the wrong way, but you get it. So what ends up happening is if your r sub u is that tangent vector, here's your point, and your r sub v is that tangent vector, then if we want a vector normal to the surface, how would I produce a normal vector? Cross product, right? So, and that's where we're going to head into for all of our applications for the next several days, is finding r sub u, r sub v, and doing cross products. So, all right, so anyway, so since both of these are tangent to the surface, then the vector n that is normal to the surface is the cross product of r sub u and r sub v. If the cross product is not 0, then the curve is smooth. If you end up with a 0 cross product, you've got an issue. Okay. Okay, so we're going to use this knowledge now to find equations of lines and planes. We've been doing this all year. Find an equation of a plane. Tangent to the paraboloid given by r of u comma v equals u comma v comma u squared plus v squared at the point 1, 2, 5. So the first thing you're going to do, find your r sub u, find your r sub v, and then you can actually, if you know you're doing it at a point, you can either plug in the point and then do the cross product, or do the cross product and then plug in the point. So either way, you're going to have to plug in the point to get your normal vector, and then use the normal vector and the point to write the equation of the plane. So let's see how well you do. I'm going to pause. All right, r sub u, derivative of u is 1. There are no u's here, so it'd be 0 and then 2u, right? Does that make sense for your partial u? Okay, and then at this point, remember, so r sub u at this point, this is an x, a y, and a z. So our r sub u at that point, you're kind of figuring out what's u and what's v, right? It's not like you're plugging in a 1 or a 5 or a 2. You're figuring out, and actually you know, like this, how do I say this? If our x is 1, then our u has to be 1. Am I thinking that right? Yeah. And our v has, if our y is 2, our v has to be 2. It's the only way for this to work. So yeah, you have a u of 1 and a v of 2. So this equates to u equals 1, v equals 2. All right, so you end up, when you plug in a 1 for u, you get the point 1, 0, or the vector 1, 0, 2. Then you do r sub v, 0, 1, 2v, and you plug in a 2 for v, and you get the vector 0, 1, 4. Are we together so far? Yeah? Okay. All right, so then your cross product, 1, 0, 2, and 0, 1, 4, so 0 minus 2 minus 4 minus 0, right? And then plus 1 minus 0?
Yeah.
What happened? Oh, okay. Yeah, hon. You sure?
Yeah.
Yes, Dorsa.
I got it messed up, but then I realized, like, you know, like the top J, like in the matrix, like the middle J,
Yes.
the top one. Like, so I thought that was a U, my handwriting. I thought it was a U and a 0. So yeah.
So this is kind of a what have we learned moment for you with your handwriting, right? So neat and clear and step by step.
It's too late for me.
Never too late.
My handwriting peaked in 08.
No, because when I started teaching, my first year of teaching, from the time I was like learned how to write until I was 29 years old, I wrote my 9s like that. And my students were like, we can't read this. Like this is just, it's craziness, right? And so they said, you have to change how you write your 9s. So I adjusted and started writing my 9s like that, and I've done it ever since, and it's really hasn't been a big deal. I also, after starting to teach, so I'm almost 30, 29 years old, right? I also learned how to put lines through Z's, right? To write my T's with a little curlicue, right? All these things that I never did growing up, you can change.
When I'm writing,
You can.
Like my T's and the plus
Yeah. Yep. I would definitely do it too.
I will.
All right. Wow, did I get us off topic? Okay. So there's our equation of our plane. Did you guys remember how to write the equation of a plane?
Yeah.
So your direction vector, right, is on the outside, and then your point is inside the parentheses with the x, y, and z. Right? Does that ring a bell?
Yeah.
If it doesn't, it's -2 times x minus 1, right? And then -4 times y minus 2, and then plus 1 times z minus 5, right? So direction vector. This is, I shouldn't say direction vector, I should say normal vector, it's a plane. Normal vector, and then point, point, point. Yeah, Laura.
We can just leave it in.
Yes, you can leave it in either form. Okay. All right, let's do another. Are there questions on this before we move on? R sub U, R sub V, plug in, cross product. Okay. All right. One last little topic, which is area of a parametric surface. Excuse me. Okay, so I see this. This is actually from the old book we used to use, the book you guys used for AP, but it's the same notation in the new book, this letter D, now representing the region in the world of U's and V's. So I guess you could say the UV plane. So anyway, if S is a smooth parametric surface, R of U comma V, defined over an open region D, there we go, in the UV plane, then the surface area of S is given by, so surface area ds, so S means surface area, is represented by the double integral over this region D, which is the bounded, like the region bounded by your U and V limitations. And then of the cross product, of the magnitude of the cross product, R sub U cross R sub V, it's the area of the region bounded by your U's and V's. So it's almost like, you know how when we were doing triple integrals and I would say, sketch the region in the XY plane first. Like always sketch the region in the XY plane so you know what you're integrating over. It's the same thing here, but now we're gonna just sketch the region in the UV plane. And you're just gonna think of it, like adjust your brain to just say UV plane, I'm just gonna draw a sketch and it's gonna be fine. So for this one, we're gonna find the area of the surface of the sphere given in these lovely spherical coordinates, R of U comma V. Oh, excuse me, sine U cosine V, sine U sine V cosine U. U is restricted from 0 to pi, V is restricted from 0 to 2 pi. Once you have this written down, we're going to talk for a minute before I set you loose. I should pause or not. Do you guys need another minute to write? Okay. So your D for this, your region D, if we had a UV plane out there somewhere, your U would be going from 0 to pi. Your V would be going from 0 to 2 pi. What shape would D be?
Rectangle.
Yeah, it's just a rectangle, right? So you're really, this is your region D. So you're just you're setting up a double integral that produces the area of this rectangle, du dv or dv du, whichever way you want to go. And then your integrand is the magnitude of the cross product. First, find the cross product. Remember the result of a cross product is a vector. And then see if you can remember how to find the magnitude of the vector. So I'm going to give you a couple of minutes to see if you can figure this out without showing you anything. Okay, so R sub U is cosine u, cosine v, cosine u, sine v, and negative sine u. Pretty straightforward. R sub v, negative sine u, sine v, sine u, cosine v, and 0. All right, so then your cross product, when you set it up, looks like that. And when you do it, you get this. Always look for things you can simplify, because on this third term, you have a sine u, cosine u in both terms, and when you factor it out, you're left with just what's equivalent to 1. So then your vector can just become that, which is nice. Has everyone gotten this far? No? Okay, I'm going to pause for another minute then. So, focusing on the magnitude. So magnitude is the big square root thing, as Jack called it, of each term, sum of each term squared, right? So that was my big square root. And then I started by just pulling a sine squared out of every term and of u and putting it out front. And then kind of looking at what's left. And then you just start kind of factoring and cleaning, right? Like, hey, look, there's a sine squared u in each of these terms. And if you were to pull it out, you'd be left with cosine squared v plus sine squared v, which is just 1, right? And then you have sine squared u plus cosine squared u, which is just 1. And then this whole thing ends up just equaling sine u. So once you've got your cross product, I went ahead and did that first and then set up the integral. You could do it in the integral, it doesn't matter. So anyway, so I did dv du. You could do du dv as long as you've got your limits matching. And then just do your antiderivative and plug in. And final answer is 4 pi. How did we do?
Terrible.
Could we have done well?
Nope.
Yes.
Nope.
Yes.
If I had decent handwriting, I could have.
Gosh. You know, your handwriting, honestly, is fine. You can go. Honestly, do you really think this is like the worst handwriting I've seen? It's
Yes.
not even remotely close. This is fine. There's nothing wrong with it. Anyone could walk in and read this.
No.
Yes, Jack.
Top.
Yeah.
I mean, that's gonna be a bad I can't read it.
Is that what you needed?
Yeah, I actually wrote down.
Oh, I'm sorry.
And when it's like 10 slides, I'm like,
Any other questions? All right, I think I have one more. Yep. Oh, review. Okay. Last thing, just for fun. Just for fun.
Whiteboards.
You want it on whiteboards?
Yeah.
Okay. Optional, independent, or on whiteboards. But I want you to determine if this three-dimensional vector field is conservative. Might have to use something that rhymes with pearl. And then, and if so, find a potential function. Curl, like you surfaces. I'll show you how to do it. Okay. So for this one, for part A, what do you have to find?
Curl.
The curl. And when you find, why won't this go down? There we go. When you find the curl, what'd you get? 0. You get, why is this, oh, it's frozen. You get 0. Okay. Which means that the vector field is what? Conservative. Therefore, there should be a potential function. The potential function. Oh, no, you didn't have to do divergence. I cut that out. I cut out parts, numbers 2 and 3 for this just because we haven't, no, it's okay. We could have done divergence, just dot product, but I didn't feel like right now. Okay, so your potential function, did you all get 1/2 ln x squared plus y squared plus z plus k? Yeah, did you really? With the, you guys all remembered your natural law? You had to do a u sub. Yeah?
Yeah.
All right, good, 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 good. All right. Hi, Alex, come on in. See if you can, see what you can get done. See if you can get like all your matchings done while you're still here. Right? You got 10 minutes to spare. Use them. This is Calc 3.
Okay.
It's hard to get them to work sometimes.
Oh,
They
okay.
actually work really hard until they have free time, and then it's
They want
kind
a
of
break.
Yeah. It's funny. They goof off way more than you guys do.
Oh, really?
Oh yeah.
Oh,
They're like.
do you want your screen recording?
Okay, so let's close. All right. Okay, I have to go grab your quiz.
Okay, yeah, that's what I was.
So I will be right back. That's off.
And then, thank you. Right,